There is a machine in your kitchen right now that has not fundamentally changed in almost 200 years. An American invented it, and a lab in Maryland may have just built the thing that finally kills it, using nothing but a metal tube and a squeeze. Because here's what almost nobody knows. The refrigerator was not invented in Europe. It was not invented in China. The first working vapor compression cooling machine was patented by a man from Newburyport, Massachusetts, named Jacob Perkins, back in 1834. He built a machine that could make ice on demand, and in doing so he handed the modern world food safety, medicine storage, and livable summers. Nearly 2 centuries later, the fridge humming behind you is still running his idea. Same core principle, same trapped gas. Same pumping heart. Every upgrade since has been paint and polish on a design old enough to predate the light bulb. And now the country that started it may be the country that ends it. Not with a bigger compressor, not with a smarter chip, with a piece of metal that gets cold when you stop squeezing it. If you're enjoying videos like this, hit the like button because these take a lot of work to put together, and subscribe so you do not miss what is coming next. The technology inside this new machine is so simple that you have already felt it work with your own hands. You just did not know what you were feeling. Scientists have understood the effect since 1805. The problem was never the physics. The problem was that every time engineers tried to build a real machine out of it, the machine tore itself apart. That is the wall. And a team in the United States just went around it in a way that sounds almost too obvious to be true. But before you can understand why your refrigerator is about to look ancient, you need to understand what is actually happening inside it right now. The old machine in your kitchen. Think about every cold thing in your life. The fridge in your kitchen, the window air conditioner, the vents in your car, the freezer wall at the grocery store, the cabinet keeping vaccines viable at your pharmacy, the cold room behind the restaurant you ate at last week. Every single one of them runs on the same idea. And it is Perkins's idea. It is called vapor compression refrigeration. And it is arguably the most important invention nobody thinks about. Strip it out of American life, and the country stops functioning inside of a week. Grocery chains collapse. Hospitals lose their medicine. Half the map becomes unlivable in July. Here is how it works in plain terms. The machine takes a special chemical gas and squeezes it hard into a small space using a mechanical pump called a compressor. Squeezing makes the gas hot. That hot gas gets pushed through coils on the back of the fridge, where the heat bleeds out into your kitchen. As the gas dumps its heat, it condenses into a liquid. Then the machine lets that liquid rush out into a wider space, and when it expands, it goes cold and greedy. It pulls heat out of the air inside the fridge. That is your cold. Then the whole loop starts over. Again and again forever. It is a clever system. It also has 2 problems it has never been able to shake. The first is the compressor. It is a mechanical part with pistons that pump up and down thousands of times an hour for years. That is the hum you hear. That is also why fridges die. Moving parts wear, bearings loosen, seals fatigue. There is a small engine running 24 hours a day, 7 days a week, 3 feet from your food, and the day it stops is the day the appliance becomes a metal box. The second problem is worse, and it is invisible. It is the gas. Those refrigerants are sealed inside the pipes. But sealed is a relative word. They seep, they leak at joints during service, and especially when the unit is scrapped. And some of them are extraordinarily destructive. Take R134A, one of the most widely used refrigerants of the last generation. Global warming potential is roughly 1,430 times that of carbon dioxide. 1 pound of it doing what 1,400 pounds of exhaust would do. Now multiply that by every refrigerator, every freezer, every car cabin, every rooftop chiller on every strip mall in America. The United States government has already conceded the point. Under the AIM Act, passed in 2020, the country committed to phasing down these high-warming refrigerants by 85% over 15 years. Read that again. The law has been written, the deadline exists, and the replacement chemistry is not comfortably better. The leading substitutes are either flammable, higher pressure, or breaking down into compounds regulators are already nervous about. So America has legislated itself into a corner. It has promised to stop using the working fluid that the entire cold chain depends on without having a clean replacement fluid to swap in, which forced a very uncomfortable question inside American research labs. What if the answer is not a better gas at all? What if the answer is no gas? And that question sent a team of researchers back to a physics effect discovered before the Civil War. A 200-year-old idea nobody could build. Take a thick rubber band, stretch it fast and hard, then immediately press it against your upper lip. It feels warm. Now let it relax back to its original length and press it to your lip again. It feels distinctly cool. You just ran a refrigeration cycle with your hands. That effect is real, and it is old. An English scientist named John Goff described it in 1805. James Joule quantified it decades later. It is called the elastocaloric effect, and the principle behind it is disarmingly simple. When you deform certain materials, you force their internal structure into a more ordered arrangement. Order releases heat. When you release them, the structure collapses back into disorder. And disorder absorbs heat, it pulls it in from whatever is touching it. No gas, no leak, no compressor, just a solid that gets cold when you stop squeezing it. For over a century, this was a party trick. A rubber band can only move so much heat, and it degrades in weeks. There was no material strong enough to do this millions of times without falling apart. So the idea sat in textbooks, filed under interesting and useless. And then, in 1959, a metallurgist named William Bueller was working at the Naval Ordnance Laboratory in White Oak, Maryland, trying to develop a better nose cone for a Navy missile. He was mixing nickel and titanium. What he ended up with was a metal that behaved like nothing anyone had handled before. Bend it and it snapped back. Heat it and it remembered its original shape and returned to it as if the metal had a memory. They named it after where it came from. Nickel Titanium Naval Ordnance Laboratory, NTNOL, is an American invention, funded by the American military, and today it is inside heart stents, in millions of chests, inside eyeglass frames, inside aerospace actuators. But its most interesting property was the one nobody had a use for at the time. When you squeeze nitinol, its crystal structure snaps into a tighter phase, and it heats up noticeably. Not by a fraction of a degree like iron in a magnetic field, by tens of degrees. Release it, and it drops just as sharply, drinking heat out of everything around it. That is a rubber band with the strength of aerospace metal. That is a refrigerant you can hold in your hand. The Department of Energy noticed, in a landmark assessment of alternatives to vapor compression, federal analysts ranked elastocaloric cooling at the very top of the list of non-vapor compression technologies, with the highest potential to actually replace the compressor. Not one of many, the top. So the obvious question is the one you are already asking. If the material was invented in 1959 and the government ranked it number 1, where is it? Why is there not a nitinol fridge in every kitchen in America? Because for 50 years, every machine anyone built out of it destroyed itself, the wall that broke every prototype. Here is the part that stopped this technology cold. The instinctive way to work nitinol is to pull it. You take a wire or a thin strip, stretch it in tension, let it go, and harvest the cold. It works beautifully. It works for a few thousand cycles. And then the material begins to fail. Think about what actually happens when you pull on metal. Any tiny flaw, a microscopic void, a rough spot on the surface, a grain boundary, becomes a stress concentration. Pull, and that flaw opens slightly. Release, and it closes. Pull again. Every cycle widens the crack a little more. It is the same reason you can snap a paperclip by bending it back and forth, even though you could never snap it in one pull. Metal does not fail from force, it fails from repetition. Now consider what a refrigerator actually demands. A kitchen fridge cycles its cooling system continuously for 10 to 15 years. That is not thousands of cycles, that is tens of millions of them. Early elastocaloric prototypes were reaching the end of their fatigue life in a matter of weeks of continuous operation. Researchers would build a beautiful machine, run it, and watch the very component doing the cooling develop hairline fractures and shear apart. There was a second wall right behind the first. The metal has to be pulled hard. Nitinol needs enormous stress to trigger its phase change, the kind of force that requires a serious mechanical drive system. So engineers were spending large amounts of energy to strain the material, and only getting a fraction of it back as usable cooling. The efficiency numbers were embarrassing next to a compressor that had been optimized by industry for 150 years. So elastocaloric cooling had a reputation by the 2010s. Gorgeous physics, broken engineering. A technology that could cool a small volume very impressively right up until the moment it tore in half. And this is where a team in Maryland asked a question so simple it sounds like a joke. What if we stop pulling it? The Maryland answer. Researchers at the University of Maryland, working in collaboration with the Department of Energy's National Laboratory System, had been chasing elastocaloric cooling for years under materials scientist Ichiro Takeuchi. They understood the fatigue problem better than anyone because they had broken more nitinol than anyone. Their insight was about the direction of force. Cracks propagate under tension. Pulling opens flaws, but compression does the opposite. It presses flaws closed. Squeeze a piece of metal instead of stretching it, and the microscopic voids that would normally grow into fractures are being clamped shut on every single cycle. So instead of thin strips pulled apart, they used nitinol tubes and drove them in compression, squeezing them along their length with hydraulic force. Same phase change, same heat released and absorbed, radically different failure behavior. The results published in the journal Science were the moment the field changed, the compression-driven system did not just survive longer, it ran with a materials coefficient of performance far beyond what elastocaloric devices had achieved before. into a range where the technology stops being a curiosity and starts being a competitor. In the same work, the team demonstrated temperature spans that put a real refrigeration application within reach, rather than the few degrees earlier prototypes managed. The architecture matters as much as the numbers. Picture a bundle of thin nitinol tubes, arranged like the barrels of a revolver. A hydraulic driver compresses them. As they compress, they heat, and a simple loop of water, plain water, the safest working fluid on Earth, carries that heat away to the coils outside your fridge. Then the driver releases, the tubes snap toward their remembered shape, go sharply cold, and the loop runs back through them to pick up the cold and deliver it to the compartment where your food sits. Notice what is not in that description. There is no refrigerant gas, there is no chemical with a global warming potential of any kind, because the only fluid in the system is water, and the only refrigerant is a solid piece of metal that never leaves the machine. If the entire thing ruptured in your kitchen, the environmental consequence would be a puddle. Notice something else. A compressor is a device that must run continuously, because the moment it stops, the gas equalizes and the cold stops. An elastocaloric core is a device that can be driven in discrete strokes, matched to demand, without a pump running 24 hours a day next to your groceries. It is fundamentally quieter, because there is no continuous pulsing mass of gas. There's a squeeze and a release. And there is one more property that nobody expected to matter as much as it does. Nitinol is recyclable metal. When an elastocaloric cooler reaches the end of its life, you do not have a technician evacuating a regulated gas into a recovery cylinder. You have nickel and titanium, and both go back into the supply chain. But the Maryland team, and the labs that followed them, realized fairly quickly that what they had built was not really a refrigerator. It was something more general than that. And it was about to walk straight into the biggest engineering crisis in the American economy. The problem that made this urgent. The United States is currently in the middle of a heat emergency, and it has almost nothing to do with the weather. Consider the data center. The buildings running artificial intelligence workloads in Virginia, Texas, Arizona, and Ohio are consuming electricity at a rate that is straining regional grids, and a very large share of that electricity is not spent computing anything. It is spent on cooling. Racks of processors generate concentrated, ferocious heat in very small volumes, and the industry currently answers that with enormous chillers and, in many facilities, with millions of gallons of evaporated water per year. In water-stressed states, that has become a political problem, not just an engineering one. Now consider the electric vehicle. Every fast charging session generates heat inside the battery pack, and heat is the single largest determinant of how long that pack survives. Manage the temperature well and the battery lasts. Manage it badly and it degrades, or in the worst case, enters thermal runaway. Currently, that management is done with liquid loops and refrigerant circuits that add weight, add plumbing, and add failure points to a vehicle. Now consider a submarine. Every compressor is a machine that vibrates, and every vibration is an acoustic signature. Silence is survival in that environment. Now consider a spacecraft, where a fluid loop in microgravity is a genuinely hard problem, and where a leak is not an inconvenience, but a mission. What all of these have in common is that the traditional answer, a big machine pushing chemical gas through pipes, is exactly the wrong shape for the problem. And a solid-state cooling element is the right shape, because it can be scaled and sited where the heat actually is. A nitinol core does not care whether it is the size of a suitcase or the size of a deck of cards. The physics is identical. You can put one against a battery module. You can put one against a rack. You can put one inside a sealed instrument that will never be serviced. This is the difference between an appliance upgrade and a platform. Vapor compression gave America the cold chain. Solid-state caloric cooling, if it lands, gives America a way to move heat anywhere, at any scale, without a working fluid that regulators are trying to ban, which is precisely why this is now a funded national priority rather than a curiosity, with work running in parallel at the Department of Energy's national laboratories, including materials research at Ames Laboratory in Iowa, and with startups spinning out of university programs to try to commercialize the cores. And that is where the honest part of this story begins, the hard road from lab to store. It matters to be straight about where this actually stands, because there is a version of this story that promises you a magnetic-free, gas-free fridge next Christmas, and that version is not true. What Maryland built and what the labs following them are building are prototypes and pre-commercial units, impressive ones, not products on a showroom floor. There is no announced date on which you walk into an appliance store and buy one. The obstacles are real, and they are specific. The first is cost. Nitinol is not a cheap metal. Nickel-titanium alloy must be melted under vacuum, because titanium will grab oxygen out of the air and ruin the composition. and the alloy ratio must be controlled to a precision that borders on absurd. A fraction of a percent of nickel shifts the temperature at which the whole phase change happens. That means specialty furnaces and specialty suppliers. A compressor is a commodity stamped out by the tens of millions. A precision nitinol tube bundle is not, at least not yet. The second is the driver. You have replaced the compressor, but you have not replaced the need for force. Something has to compress those tubes with real hydraulic pressure, millions of times reliably in a sealed box in someone's kitchen. That driver is now the component with moving parts, and it inherits the durability burden the nitinol just escaped. The third is fatigue, still. Compression bought an enormous extension of life, and that is the breakthrough. But an appliance manufacturer will not ship anything into American homes until it has hard data showing survival across the full service life with warranty exposure attached. That data takes years to generate, for the simple reason that you cannot fast forward a decade of cycles without changing the conditions you're testing. And the fourth is the incumbent, which is a genuinely excellent machine. The vapor compression system has had a century and a half of relentless optimization by an industry with enormous manufacturing scale. Beating it on paper in a laboratory is one thing. Beating it on cost per unit of cooling on a factory line at consumer volume is the actual contest. None of that erases what happened here. A 50-year wall came down because a team stopped pulling and started squeezing. That is what a breakthrough usually looks like. Not a new law of physics, but a change in direction that makes an old law finally usable. Every technology you rely on went through this exact stage. The first computers filled rooms and cost fortunes and were owned by governments. The first solar cells were a space program luxury priced far beyond any practical use, until manufacturing scale did what manufacturing scale does. The pattern is always the same. A thing works in a lab and looks impossibly expensive, and then it does not. So sit with the strange symmetry of it. An American in Massachusetts invented the machine that made cold a utility. An American Navy lab in Maryland accidentally invented the metal that might end it. And a university team a few miles from that same lab found the one direction of force nobody had properly tried. One day you may open a refrigerator and hear nothing at all. No hum, no click of a compressor kicking on at 2 in the morning. Just a box that stays cold because a piece of metal inside it is quietly being squeezed and released, over and over, remembering its shape, which leaves one question worth arguing about. The compressor is not only in your kitchen, it is in your car, your office ceiling, and the building down the street. So if this technology scales, which of those goes silent first, and which one are we going to miss the sound of? Tell me in the comments. And if you want more stories like this one, hit like, subscribe, and turn on notifications so the next one finds you.